We often do mathematics without knowing the reason why we are doing. As a result, we do not see any reason, goal or objective. Hence, mathematics becomes boring or difficult. The mathematics of general relativity is nothing extraordinary but an assimilation of the mathematics that you already know plus a little bit extra. The reason for considering the mathematics of GR as difficult is not knowing why you are considering or why you are doing it and what is the relationship between those abstract mathematical entities with the concepts of general relativity. Is it visible? Things become much more clearer when you see the relationship, and then when you study them, you know actually what those concepts would lead in general relativity. Welcome to the second episode of the Mathematics of General Relativity, where we are taking a step further to know more. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to episode 2 on how to learn the mathematics for general relativity. In the first part, what we have covered here is a quick snapshot, I would say a quick recap for those who have missed. Anyway, I have put it up in the I button and created a separate playlist through which you can go and recap the earlier videos. So in the first episode, what we first came to know is about this, that the mathematics of general relativity or the overall understanding is more of a geometric understanding. So it is a complete paradigm shift, an exquisite departure from the conventional Euclidean flat space-time to something which is called a curved space-time. And we have seen that how the relativistic effects of special theory of relativity is not that important, but what is important is the geometry and the curvature of space-time, which is predominant in learning the theory of relativity. As a result, we saw there are a lot of mental preparations. I would see a paradigm shift in terms of thinking, because here you have to think more abstract. The visualization power should be more, and because it deals only with geometry, so as you understand, geometry means visualization. So as this is concerned with geometry, so you will start to think, or you will be tested with more abstract thinking, and geometry is all about visualization. Hence we call it that you need to have an intuitive mind, or you have to think in terms of your intuitive power rather than mathematics. Obviously mathematics is there. In the last video, I also talked about why the methods and understanding of the calculus, particularly partial differential equations, are very, very important. If you go to the first video, you will see there are enough amount of examples, methods, equations which shows that partial differential equations holds the key to unlock the mysteries of general relativity. As Einstein's field equation are a set of 16, later reduced to 10, a set of nonlinear partial differential equation, geodesic equation, Christoffel symbols, Riemann curvature and whatnot. These are all very, very important, and our understanding of partial differential equation should be very important. You also saw that different type of equations which led to the formation of the core idea, that is the metric tensor, also comprises of lot of partial differential equations. So the basic idea is that you need to learn more and more PDEs than the ODEs. And for that, we also saw in the last video that there are a lot of books, and I have actually given a few books with the basic calculus on ordinary differential equations, followed by partial differential equations, the best books in terms of partial differential equations, what is the sequence, what it lead to, and things like that. So learning ODEs is primarily important, and that is what we covered in the first video. Now when we come to today's video, that is the part 2, what we see is that those who already know general relativity, or those who are thinking to learn the mathematics, you must have seen matrices like this or this. This is the metric tensor, and it is the stress energy momentum tensor, which we are going to evaluate later. But as you can see, this is a 4 by 4, a kind of a matrix which has got certain values and indices. You must have also seen these things. And these are basically matrices which carry on with different operations like addition, subtraction, etc. And these are very common in terms of what we call linear algebra. So the question that comes to our mind is that what is the relationship? I'm going to say what is the relationship between the matrices that are there in general relativity followed by the ordinary matrices which we see in the graduate books of linear algebra. And most importantly is linear algebra important in understanding general relativity? Obviously yes. But if you ask anybody, they will say yes, without giving the proper reason or showing how the concepts of linear algebra relates to that of general relativity. And that is how things become much more interesting, visible right in front of you when you see that the concepts that you're reading in linear algebra, doing the mathematics day and day and cracking your head actually leads to something which is the beautiful theory of Einstein's general theory of relativity. So we come to the next part of our video where we are going to see why do you need linear algebra, and this is specific, why do you need linear algebra for general theory of relativity. So we start with the usual question why, and we come to this kind of a definition because linear algebra provides a very steady and a rigorous framework for describing velocities and other directional quantities. Now remember that when we go from matrices to tensors, they are actually represented in terms of matrices. So the energy density, momentum, etc. all are basically written in matrices, and that is why we need linear algebra. More than that, as you can see here, that the metric tensor is nothing but it can be called as the inner product of the tangent spaces of a manifold. Don't worry if you don't understand those technical jargons, you can just leave that. But you can understand what is an inner product, and it is actually used to compute distances and angles. I will show you in a pictorial description. Also, the most important, the Ricci tensor, which is actually obtained by contracting the Riemann curvature tensor because it takes certain indices which are repeated. This is also considered as some kind of an operation in linear algebra. So I hope you're getting the point that how linear algebra is actually showing our path, which is leading to opening the door of the mysteries of general relativity. Now here you can see this is a metric tensor, and there are certain common components. Well, I have shown this in my earlier videos, which is called Einstein's field equations. However, you can cancel out those components, and here we come that general relativity is the metric tensor is basically the key element which captures what are called the angles, curvature in Euclidean geometry. So from here what we can get is that if we cancel out, then 16 components get reduced to what we call 10 set of equations, 10 partial nonlinear differential equations. And that won't be possible without linear algebra. And also we find that the metric tensor is a symmetric tensor. That means G mu nu would be equals to G nu mu. And symmetric tensor means that whatever the way you are measuring the tensor, whether be it in the clockwise or anti-clockwise, the result would be the same. So again, linear algebra, symmetric tensor, these things all come. And just as I told you that it captures all the notions as time and distances, you can think metric tensor is something which is measuring a kind of a curvilinear grid. And those points are same like Euclidean points, and you want to measure how distance it is, what is the volume, what is the angle, how far it is. Although it is not that simple, but this is an analogy which will give you an understanding of how Euclidean geometry and metric tensor, more or less they are something similar, something which gives the notion of capturing the distance, time, curvature and angles. Now this gives you an idea that the importance of linear algebra and how it relates to the physical concepts of general relativity. However, there is one very important concept which comes across, and that is called the stress energy momentum tensor. Remember, this is the safe house where energy, density, anything related to matter is stored over there. And you can see this is already a matrix. So how would this be possible without linear algebra? So it involves components of vectors such as mu nu. and it encodes the metric tensor demonstrating multilinear algebraic operations. The next thing which becomes very important is what is called a vector space. And we all know about vector space when we are learning linear algebra, but this is vectors in curved space. Think of this kind of a space which has got these vectors, and these vectors are just vectors. I mean to say they just measure something in terms of magnitude and direction. So we can say that a space where the vector lies and where the vectors can be added or scaled. But in case of general theory of relativity, you see that it deals extensively with vectors in curved space-time. And it is all because of this curvature that we are looking into the mathematics in a different way. The concept of vectors and vector spaces are very fundamental in linear algebra, but here it takes place of a different kind of a vector space. I will talk of that. So vector is a four-dimensional space-time, and it can be represented as this. But in vectors in general relativity, as I told you, it is an object that exists in the tangent space. That means those tangent just kisses through one point on the tangent space, and the collection of all these spaces over the manifold forms a more complex structure which is called a vector bundle. We are not going to look into what is a vector bundle, but as you understand, the vector space in linear algebra helps to modify, I would say extend those concepts into tangent spaces, and then they become a vector space. So mathematically what we can say is that if I get a vector something like this, and in space-time it might represent the forward velocity of a particle, and it looks something like this, although this is not accurate, I will tell you. These things 1, 0, 1, 2, 3, these are called the spatial coordinates, and this d tau is nothing but the proper time. We also get a concept which is called an inner product, which is very common in calculations of linear algebra. And in general relativity, the inner product and two vectors this and this is given by this. And obviously metric tensor, because it forms a part of the inner product, becomes very important, and this shows now you can it is visible that you can see the concepts of linear algebra, how it is showing the concepts of general relativity. So from here what we see is that the vectors in general relativity is denoted as this. The length of a vector again is given by a norm, so it again takes into account the concepts of linear algebra. You can also diagonalize in a local inertial frame the metric tensor, which more or less looks like this. And as you know, the metric tensor g mu nu is definitely the inner product of this. And this is something very interesting. When we take a differential volume of a particular object, then what we get is the determinant followed by, I'm not telling these are Levi-Civita connection, but anyway, so the change in volume is not only the determinant of the forward transformation, but also determinant of this. I know this part is not very clear, so if you really want to know how the determinant of a matrix and the volume element and volume forms are related to each other, please go and watch this video of mine, General Theory of Relativity in Physics for Students, playlist of General Relativity, lesson number 12, where you can find volume change, volume form, sectional curvature, and how these things relate beautifully to what is called linear algebra. So from here we can find out that all these concepts are very inherent, and you need to have a very strong understanding and very strong foothold of linear algebra. So this part of the video actually shows the physical concepts of general relativity, along with that the abstract mathematical concepts of linear algebra, which you solve on paper to get good marks in the examination. However, this leads to the beautiful theory of general relativity. Now this might be very mathematical in nature, but there is a question which might be going in your mind. Which concepts of linear algebra are related to general relativity? We have actually talked into our mathematical equations, but a basic clear understanding would help us to make things much easier. So first is that we have seen vector spaces because they form tangent spaces in manifold. The second thing which would be required are called matrices and matrix operation. So all the reduction and the vanishing of the indices, etc., the covariant, the contravariant tensors, which we will see next in the coming episodes, all are basically matrices and matrix operations. So without the matrix operation, without understanding the matrix operation, it won't be possible. The third thing which is very important is called the inner product. And inner product not only for general relativity, even if you have seen my a few days back I have made a video on quantum mechanics, the linear algebra, how it is in quantum mechanics. It is too important. So for allowing the calculations, we form the metric tensor, and it is basically important for inner product and norms. The fourth thing which comes is what we call diagonalization, although in literal English this is wrong, and orthogonality, this is also not right. So orthogonality and diagonalizations actually helps to simplify things in local inertial frames. We have also seen that linear transformation, that how things transform in Christoffel symbols, etc., becomes extremely important in terms of linear algebra. Now there's something which is called a symmetric and an anti-symmetric matrices. You see that a matrix is symmetric, and if it is symmetric, it has got certain characteristics, certain features, which is the metric tensor. And the electromagnetic field tensor, this F mu nu, this is again as an anti-symmetric matrix tensor. So there are certain features. So all these are because of linear algebra, which is helping us to understand better the concepts of general relativity. The next thing is obviously, which you have seen, that volume form, volume element, these are very much related to knowing and understanding how to calculate the determinant of a matrix. And then comes what are called eigenvalues and eigenvectors, very much important to describe how space-time is curved. And finally what we call is the linear transformation. That means it would require a lot of transformation from one coordinate system to another, from Euclidean system to non-Euclidean system. So we understand the value and the importance of linear algebra. Mathematically, what are the concepts? And in English, or in pure, I would say in simple terms, what are the concepts of linear algebra that carries relevance to general theory of relativity? Now the question is that how to learn these concepts. What are the books? Coming up into the next part of our video. There are a lot of books in linear algebra, and it is very important and difficult sometimes for you to make a decision which book to go for. And in this video, in the next part, I will be telling you and enumerating the details of the books of linear algebra, the easiest one, and which you can quickly learn, and things become much more promising. So the first book, and I will tell you later the sequence, is this one, Elementary Algebra by Anton Rorres. The customer review of Amazon shows a 5-star of 63%. However, I think that it should be more than 90%. This is one of the best books because more than understanding the calculations of linear algebra, the geometric intuition becomes easier. Once you visualize things, the abstract entities of mathematics starts talking to you. And this is one of the best books till now, and you should have it. Now, before I go ahead and explain you the content and why it is important, if you have watched my earlier videos on what are the features of a good book, I've always talked that there should be certain objectives, clear, crystal clear, which would be before the reader. And fortunately, this book of Anton Rorres carries that feature. Now you see here, you can just read the underlined portion. Linear algebra, the main pedagogical goals is to give that linear algebra is a cohesive subject and not simply a collection of definitions and techniques. Also, you can see that it targets for a smooth transition, because the transition from Rn to general vector space is difficult. For many students, considerable effort is devoted to explaining the purpose of abstraction and helping the students to visualize abstract ideas by drawing analogies to familiar geometric ideas. I mean to say, this is fabulous, this is tremendous, this is one of the best objectives that an author can give to the student. That in order to explain the transition, it becomes very important to visualize abstract ideas. And if you see right at the beginning here, I told that geometric intuition is something that you get. As you see in the mathematical part, it has written proofs are presented in a patient style that is tailored for beginners. That means if you're a beginner, then you can learn this book. The proofs are pretty easy. This text is also designed to serve the students of need in engineering, computer science, biology, physics, business and economics. That means if you're not only coming from the mathematics background or physics background, you're coming from any background, this book is meant for you. And last but not the least, most importantly, it gives you a sense of mathematical history and to convey that real people created the mathematical forms, and that is why there are a lot of historical notes and reference which makes the learning even more interesting. Now, if you see that the author has also given about the exercises, there are graded exercises, true, false, supplementary exercise, and also there is a supplementary material for MATLAB, etc., and the website is given. What else would you require for a book to be so beautiful? So here is a quick snapshot on how the book looks like. So it starts with the systems of equation and matrices, and it first introduces to systems of linear equations, and then it gets step by step and so on. So as you can see, the content of the book is very crisp and to the point, and it actually shows from chapter 1 up to chapter 10. It contains Euclidean vector spaces, general vector spaces, etc. Also, you can see this is how they are being arranged, the lecture wise. So if you are a teacher, then you can take down the lectures and teach your students, and if you're a student, you can understand what is the plan of the book to read. And most importantly, the favorite part of the book is this. It is around 1276 pages. That means it teaches you assuming that you know nothing. And that is why the number of pages are more. And this is one of the key features of any good book, assuming that you know nothing and starting from ground level zero. These are some of the photographs, although they have just taken a quick snapshot, so apologies for the bad resolution. You can see here that how the matrices and they are being underlined and colored, etc., to make things much more easier. These are some of the historical references, and most importantly, you will see there is a concept review after each and every chapter. This is tremendous, and this is very much required for learning. You will see there are certain exercises which are given, followed by the answers. So all in all, I'm going to say this is just an encyclopedia which will give everything that you need. And at the end of the book, it gives you how to read theorems and an appendix on complex numbers, because this will be required. So all in all, this is one single book, I would say, one book which is a one shop store, what we call, will give you an understanding of everything. Coming to the next is a very legendary book of linear algebra by the author Gilbert Strang. Don't worry about the customer reviews, but I can say you Professor Strang's renowned book begins by introducing the concept. So again, it is a book which assumes you nothing, and it engages into classical linear algebra, subspaces, least square. I think this is a very renowned book. It's a good book, and most of you have gone through. So this is another great book in terms of learning linear algebra. These are the table of contents, which I think you already know. So I really don't need to go step by step. So what I can say is that the book is good enough to build the concepts of linear algebra, and after reading this book you will get enough amount of motivation and concepts of learning linear algebra right from zero. So here are a few of the snapshots how the book looks like, and this has got beautiful diagrams, and it is followed by what is called challenge problems you can take up, and followed by the review of the key ideas and some of the worked examples. So this is a very good book to start and learn linear algebra. The next book is a little bit, I would say, unknown, and it is coming from Sheldon Axler's Linear Algebra Done Right. So this book is also good because the author actually builds up on topics like theory, field basis, dimension, projections, and so on. But this is a very exhaustive book. Let me show you quick snapshots of the book. So it starts with vector spaces, subspaces, finite dimensional vector spaces, then goes into linear maps, invertibility, and isomorphic vector spaces, followed by eigenvalues, eigenvectors, and invariant subspaces. So it goes step by step. I'm going to say there's nothing to worry about. After that, the book covers operators and inner product spaces. It also covers complex vector spaces which will be required, followed by traces and determinant, and so on. So it's a good book, quite good, comprehensive, smart enough to give you an idea on linear algebra. The next book is quite a popular one. It is called Schaum's Outline of Linear Algebra. And you know, the good part of the book is that this book begins at the higher secondary level, and you can do your exams like UPSC, GRF and NET. And if you are a self-learner and if you're a beginner, this is the best book for you. And as you see, if you need assistance with the GRE and subjects like that, this is the one. And I personally speaking, I paired with Linear Algebra by Freiberg, but I found that this Schaum's Outline is a great book to go through. Here are a few contents and I would say a few snapshots. So it starts with vectors. It's same as the earlier book of Axler's. So, and then it goes into eigenvalues, eigenvectors, and so on. The good part of this book is that it gives you quite a lot of diagrams, and most importantly, you see that it has got supplementary problems followed by answers to the supplementary problems. So it is quite a good one which you can read and understand. You can do the exercises and you get an expertise on that. The next book is something which is a little bit unknown, an unfamiliar book. It is called Linear Algebra, an Introduction by Bronson and Costa. I found this book very clear with a lot of examples, etc. And this is a very short, I would say crisp content of what the book comprises of. So you can also go through this. I found it, great because it contains all those things in a nice, precise manner with a lot of examples coming up. Now, once you have got so many books, you must have a question in your mind that which one to go first, which one to go second, and what is the sequence of reading these books. Coming up into the next part of the video, I will show you the sequence in the sense that as a beginner, which book you should start with. So the first thing I would like to tell is not Gilbert Strang, but this book. That would be part 1, because it will give you a very clear geometric visual understanding of linear algebra. You can go second with Gilbert Strang's book, and then you can start reading Schaum's book because it has got a lot of fully solved problems and certain examination things which will be good. Then you can go with this book, Linear Algebra by Bronson and Costa, then Linear Algebra Done Right, and another book which I have not shown in details but a little bit advanced book, that is by Sir Lang's Introduction to Linear Algebra. So that gives you a fairly good idea about linear algebra, books, sequence, concepts, how it is related to general relativity, and why you should go ahead and learn linear algebra. So that's all for today's video, part 2. We end here, and thank you very much for watching this video. If you have liked, please do not forget to hit on the subscribe button and click on the bell icon and click on all to get all the notification from Physics for Students. You can write to this email ID and you can subscribe to my other channel, General Relativity Explained, which is exclusive for videos only on Einstein's General Theory of Relativity. Further, you can follow me on my Facebook, LinkedIn, Instagram and Twitter account. Physics for Students will keep on surprising you with more such interesting videos. We completed the second part of how to learn the mathematics of general relativity. Coming up very soon is the third part on how to understand the mathematics of general relativity. I hope you're liking this series. Please put up your comment, and still do you find general relativity and the mathematics to be difficult? Please let me know. I will be soon back, but till then, goodbye.